In this video, we'll look at yet another way to determine whether a series converges or diverges. In this case, we're going to be looking at alternating series. I want to point out that this is a pretty narrow set of series that this will work on. And I'll define what an alternating series is in just a minute, but hopefully this video won't be too long because this isn't going to be quite as widespread of a test to use as, say, like the direct or limit comparison test. But an alternating series is just a series where the terms switch between positive and negative. So an alternating series has terms that switch back and forth between positive and negative. The alternating series test is pretty simple. I'm going to jump straight back into it. So the alternating series test says the following. The actual test looks like this. So if we have an alternating series that looks like the following. So if the alternating series given by the following so it's going to look like the sum from n equals 1 to infinity of -1 to the n plus 1 times b sub n. And that -1 to the n plus 1 is what's going to ensure that our signs switch back and forth. So we're going to assume that b sub n by itself is always positive. And this is the thing that makes everything switch back and forth. So it would look something like the first term would, when we plugged in n equals 1, the b sub 1 term would be -1 to the 1 plus 1 power, so it would be squared and would be positive. So we'd wind up with b1 for our first term, and then we'd plug in n equals 2 for our second term to get b sub 2. When we plug in 2, this power up here would become a 3. -1 cubed is -1, so we get minus b2. Then we get plus b3. Then we get minus b4, and so on and so forth. Might as well add a few more. So that's what the series would look like. This is what we mean when we say it alternates, the terms alternate back and forth between positive, negative, positive, negative, positive, negative, and so on. And we're assuming that all the b sub n's are greater than 0. So if we have this series and it satisfies the following conditions, so if this series satisfies condition 1, that b sub n plus 1 is always less than or equal to b sub n for all n. So basically, the b sub 1 term, neglecting, so forget about the plus or minus sign. B sub 1 is larger than b sub 2, is larger than b sub 3, is larger than b sub 4, and so on. So basically, as you progress down this list, the b's get smaller and smaller. So b sub n plus 1, the next term is always less than or equal to the current term. So each one of these terms successively has to be smaller than the term, smaller or equal to the term that came before it, I should say. So if that condition is met, and secondly, if the condition is met that not only do they get smaller, but eventually they go to 0, so meaning the limit as n goes to infinity of b sub n is 0. If those two things are met, then the series has to converge. So if we compare this to some of the stuff we've talked about before, we saw before that these terms going to 0 is a necessary but not sufficient condition to ensure that a series is going to converge, right? We looked at that with the series of, or with the list of all the different functions that we see going to 0. So 1 over 1 over the log of n, 1 over the square root of n, 1 over n, 1 over n squared. We looked at all of those and compared them and saw that they all go to 0, but not all of them necessarily are terms that if they show up in your series will ensure convergence of your series. Basically, you need things that go to 0 more quickly than 1 over n. In this case, we're relaxing that. Basically, when it's alternating, as long as these terms go to 0 eventually, and each term, again, successively is getting smaller and smaller and smaller, which is usually satisfied anyways. But now we're basically saying if the terms go to 0, it's going to converge. Doesn't matter if they go to 0 slowly or quickly, it's going to converge. The idea behind this is that the alternating allows for a lot of cancellation. So let's imagine that I have my number line here. Maybe we start at, here's 0 on our number line. And let's say the first term that we start with is b sub 1. So b sub 1 shows up here. Here's our plus b sub 1. So this distance is our plus b sub 1, our first term, which again, let me zoom out so we can see it all at once, which I'll remind you is this positive term. The next term needs to be smaller than b sub 1, and we're subtracting it. So basically, I'm going to go from here the first time and go to b1. Then from here, the next, so this is at n equals 1. Let me zoom in a little bit so we can get this a little better. This is n equals 1. There we go. The next one, I'm going to subtract b2, but b2 is less than b1. So that's going to put us down to this position. This point right here would be where we're at after b1 minus b2. It would put us right here. So here is after 2 steps. We're down there. But then b3 has to be positive again. So we'll go from here back up in this direction. But again, b3 has to be less than b1. So that would put us, here's the b1 minus b2 plus b3. And we're at n equals 3 steps in. So what's happening is each of these arrows represents the length of b1 or subsequently b2 or b3, and we're adding them up. And what we're going to do is we're going to start to zero in because each one of these arrows successively has to be shorter than the arrow before it. And secondly, the arrows are eventually going to have a length of 0. So this next step would come back this way a little bit, then the next step would come back this way, then the next step would come back this way, then the next step would come back this way, the next step would come back this way, next step would come back this way. Even that's probably too long. Whoa. And we're eventually, you can see, going to converge to some point right here. Here's what the sum of that series will eventually be. After n equals 4, n equals 5, n equals 6, n equals 7, n equals 8, n equals 9, and so on. So as we add more and more terms, we're basically going back and forth, but also zeroing in, because each time we go back and forth, that jump has to get smaller and smaller. This is telling me that each successive jump has to get smaller, and eventually the size of the jumps is going to 0 as we go back and forth. And so we'll eventually zero in on one particular value. So this is kind of the idea behind how this type of alternating series will work. Okay, so for example, let's do a specific series here instead of hypotheticals. And let's say that we're looking at the sum from n equals 2 to infinity of -1 to the nth over the natural log of n. And the only reason I'm starting at 2 instead of 1 is because if I started at 1, the natural log of 1 would be 0, and we would get a 0 in the denominator here. So I'm starting at 2 instead. So the fact that we're starting at 2, just keep this in mind. It's not going to affect, this doesn't matter in the sense, it matters to ensure that we don't get a 0 in the denominator, but it doesn't matter relative to how we defined our alternating series. The fact that I'm starting with a 2 here instead of a 1 makes no difference. So keep that in mind. So here is what it looks like. our b sub n's are switching back and forth because of this -1 to the n. So it is an alternating series. As n increases, the natural log of n will get larger. And as the natural log of n gets larger here in the denominator, the overall term will get smaller. So I'm also satisfying this condition, condition 1, that each successive term, if the denominator gets larger each time, then each term will overall be smaller. And then we also know that the limit as n goes to infinity of natural log of n, the natural log of infinity, this is going to go to infinity. We'll have 1 over infinity. The whole thing is going to 0. So we've also satisfied condition 2. So basically, that's what the two conditions look like. Let's write them out explicitly. So first, this is alternating because of the -1 to the n term. Condition 1, b sub n plus 1 is indeed less than or equal to b sub n, because if I look at 1 over the log of n plus 1, that's always going to be less than or equal to 1 over the log of n itself. So basically, each one of these terms is going to be successively smaller as n increases. So we've got that. So this is for all n. So hopefully that is obvious by observation, that as we natural log is a strictly increasing function. As we increase its argument, it will get larger, but if that whole thing is in the denominator, then the overall function will get smaller. And the second criteria is that the whole thing goes to 0. So the limit as n goes to infinity of 1 over the natural log of n, it does indeed equal 0. Right? It's 1 over infinity, basically. So the whole thing is going to 0. Because of both of those, by the alternating series test, the series converges. Let's just write out the series. The sum from n equals 2 to infinity, -1 to the n over the natural log of n converges. I don't know what it converges to, but I know it converges because it satisfies these two criteria. Okay, so that's makes these pretty simple. But again, they don't show up a ton because they require this -1 to the n type term to show up in order for them to alternate. Let me talk about one other important thing related to alternating series, and it's that we can basically estimate how much error, if we truncate the series and don't have it be an infinite series, so we don't sum all the way to infinity, but if we truncate it at some point, how much or how far off is that answer from the true sum of the infinite series. So this is the alternating series estimation theorem. Okay, so let me just write the theorem out, then we can kind of explain and think about what it's telling us, and then maybe we can try to apply it to an actual example. So the alternating series estimation theorem says that if the sum of our series, so if S is the true sum of the sum from, again, it's -1 to the n plus 1, b sub n, again, assume that in this case, whatever, might as well write it here, n equals from 1 to infinity. So if this is this actual true sum of the series, if it's S, and this is happening because b sub n is always greater than 0, and we have this alternating series. So if S is that sum of an alternating series, with those two conditions satisfied, with condition 1 and condition 2 satisfied, to ensure that it does indeed converge, then it turns out the residual, which is the error basically, it's what we called R sub n in that previous video. I'll do some absolute values around it because we aren't going to know if we're overestimating or underestimating, but just how far off we are. So R sub n, which is the difference between the true value and the nth partial sum after we've truncated, is always going to be less than or equal to b sub n plus 1. So what I'm suggesting is basically the amount of error in your sum. If instead of having the sum go all the way up to infinity, if we truncated it and said, let's only go up to n terms, let's truncate this after the first 10 terms, for example. If that's the case, then the amount of error that we would have after adding up 10 terms compared to the result we would have gotten hypothetically if we'd gone all the way to infinity, that's what this residual is, it's going to be less than the magnitude of the 11th term in the series of the b sub n 11. That's the idea here. And again, if you come back to this picture, it kind of tells you, right, if this is where my sum s is, and I know that basically, so let's say I've only added up the first two values. So I'm gone up to n equals 2. So here was my first term that I added, here was the second term that I added, and here's where I am. That would mean that this distance right, let's do it in this distance right here would be my R sub n. Right? That's the residual. That's how far off I am after 2 terms. That's how far off I am from the true value. This distance has to be less than b3, which is this length right here. Right here, that distance is the distance b3. And this, really, I should write it as R2. The error is going to be less than whatever the size is of the next term that we would be adding in. And that makes sense because these have to be decreasing so that we are continually zooming in. At any one of these points, I'm going to be off by a distance from the true value that's less than the length of the next arrow. That's all this alternating series estimation theorem is telling us, that as we're going back and forth, this is the length of the next arrow as I went back and forth, we're going to be off in our sum by less than that amount. So we can use this to approximate a sum up to a certain number of decimals and figure out basically how many terms we need to include to, have our estimate be within a certain number of decimals of the true value of s, etc. So let's look at an example, and hopefully this will again make a little bit of sense. But hopefully this picture makes sense. The amount that we're off by after the sum of the first 2 terms, which is this distance here, that's the residual, it has to be less than the magnitude of the next arrow that we would add as we go back and forth. Each of these arrows, so the length of this first arrow was b1. Then from that I subtracted b2. Then we added b3. Then I'll subtract b4. And at this point, after 3 terms, this is my residual, the distance between here and here, and that's going to be less than the length of the next arrow, which would be b4. And now I'll be off by less than the distance of the next arrow, that would be b5, and so on and so forth. Basically, it's just a factor or an artifact of the fact that we're zeroing in on the correct answer, and each one of these arrows is successively getting shorter and shorter and shorter. That's all that this boils down to. So let's use this theorem to approximate the following. Let's say I want to approximate the sum of, let's do the series, I want the sum from n equals 1 to infinity of -1 to the n over 2n factorial. And I want to approximate it to be within 4 decimals. I shouldn't say within 4 decimals. Approximate it to 4 decimals. That makes more sense. Okay. First, I want to verify that conditions, so it's alternating. And indeed, conditions 1 and 2 are satisfied. Basically, my argument is that as n increases, the denominator will strictly increase and the overall fraction will decrease. And similarly, as n goes to infinity, the denominator goes to infinity. We have a constant 1 over infinity, which is going to 0. So we've satisfied conditions 1 and 2. And now we just need to look at this rule right here. So the amount of error, R sub n, is always going to be less than or equal to b sub n plus 1, according to the theorem, right? Cut out the middleman here. The amount of error is less than or equal to the n plus first term in this series. So what we need to do, if we want to ensure that we're getting 4 decimals correct, is we need to find a b sub n plus 1 that's smaller than basically 0.00009. Basically, we want it to be less than or equal to like a 10 to the negative 5th. We don't want this to change until the 5th decimal place. So we want our b sub n plus 1 to be less than or equal to 10 to the negative 5th. By the time it gets down to 10 to the negative 5th, this thing will only be changing the 5th decimal place, and we won't have to, and we will be ensured that we have it correct up to 4 decimals at that point. So that is our idea here. So let's look at n equals 1, the first term. And before I do this, I think I want to change this. Let's change the power here. Just to make it a little bit easier, we'll have to deal with slightly fewer negatives. Let's change this to n plus 1 in the power up here so that the first term is positive when n equals 1. This will just make it a little bit easier. We'd get a different number if I'd left it as just n by itself, but this will just be slightly simpler. We'll have fewer negatives to keep track of. So when n equals 1, I want to look at what is the first term that we're going to get. So what is b sub 1? B sub 1 is going to be, as we plug in n equals 1 up here, we'll get negative 1 squared, which is positive. So I'll just have 1 on top over 2 factorial. So I just get 1 over 2 factorial. And again, the b, if you want to think about it, remember the b itself is separate from the negative 1 to the n plus 1 term. So the b sub 1 is just 1 over 2 factorial, which is 0.5. 2 factorial is just the number 2. It's 2 times 1. So we get a half, 0.5. And that means that the sum, s sub 1, the first partial sum, is also just 0.5 because we've only had that one term added in. As we go to the next one, n equals 2. What is b sub 2 going to be? Well, that's just going to be, again, forget about the negative sign. We'll take care of that when we start adding these up. But b sub 2 is just 1 over 2 times 2 factorial. So 1 over 2 times 2 is 4 factorial. So 4 factorial is the number 24. 4 times 3 times 2 times 1. So this is 1/24th, which is equal to, as a decimal, I'm just going to plug this in on a calculator that I've got here at 0.0416, repeating. And if I do my S2, I need to basically take the 0.5 and subtract off the 0.0416 repeating. And we will get, hold on, oh no, is my calculator on the verge of dying? I have a backup here. That one's dead. So here, let's do this one. 0.0416 repeating. And we get, in this case, approximately 0.4583333. So 3 repeating. Let's look at n equals 3. The third term will be 1 over 2 times 3 factorial, so that's 6 factorial. 6 factorial is a large number. 6 times 5 times 4 times 3 times 2 times 1. So it turns out it's going to be 30 times larger than that number, the 6 times 5 times 4 factorial. And that gives me 720 in the denominator. So 1 over 720 is approximately 0.00138 repeating, and I guess it's exact if we do the repeating. And that will give me the third partial sum. So I had this one was positive, this one was negative, the next one's positive again, so it's 0.5 minus 0.0416 repeating plus 0.00138 repeating. And at that point, what do we get here? This is going to be about, let's see, so get the answer that I just got. This one, sorry, taking a minute on the calculator here. So I want this one plus this one, hit enter, and I get, let's see, about 0.45972-ish repeating. Okay, let's go to n equals 4. And notice, I know that I still need to keep going because my third term here, b sub n, or b sub 3, is not smaller than 10 to the negative 5th yet. I'm still at 0.001. This is on the order of 10 to the negative 3 right now. But by the time we get to b4, what do we get? That's going to be 1 over 8 factorial. 1 over 8 factorial, that's the same as 8 factorial is 40,320. That's a tiny number, so 1 divided by 4,320 is, and down to the number on the order of 10 to the negative 5th. So this is about 2.48 times 10 to the negative 5th. So we're down to a tiny number that is now going to only affect things in the 5th decimal place. And so I said less than or equal to 10 to the negative 5th. I really should have said on the order of 10 to the negative 5th, so that it's not going to affect things, but this will be enough to ensure that we're there. The next one after this will definitely be less than 10 to the negative 5th. But you'll see here, this will not affect that 4th decimal place. So I'm going to subtract this term in. So it's S4 is the positive 0.5 minus 0.0416 repeating plus the 0.00138 repeating. And now we're going to subtract off roughly 0.0000248-ish. And this will give us, when it's all said and done, I'll have this minus this guy on the calculator, hit enter, and we are at 0.45969. So I'll round that to a 7, 4597-ish. And at that point, the numbers after this are basically terms that are going to be our rounding error. We don't care about them. Don't even know why I'm labeling them. So this is what this term is approximately. By the time we get to the fifth term, when n is equal to 5, b sub 5 is going to be 1 over 10 factorial. 10 factorial is a huge number. So 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. It's on the order of almost 4 million, so 3.6 million. This is 1 over 3,628,800, which is definitely less than 10 to the negative fifth. And so this term will not add. This won't change the fourth decimal place. We only needed the first 4 terms to get 4 decimals of accuracy. So this is the idea. You can tell you're getting close once you get down to the order of basically 1 decimal beyond. So if we want 4 decimals of accuracy, keep in mind it's b sub n plus 1 that has to be less than or equal to 10 to the negative fifth. That means the current n often can be on the order of that same number, right? So here, the fourth one, we had a number that was in the ballpark of 10 to the negative fifth, and by the time we went to the fifth one, we got something that was less than 10 to the negative fifth. It wasn't going to be contributing anymore, so we don't need to include this term in our sum. The first 4 terms were sufficient. And here is our approximation, accurate, at least having rounded to 4 decimal places. So this is the idea of how we can use these. They're going to show up in a limited number of scenarios, but the main takeaway from all of this should be when you have a non-alternating series, the terms in the series need to go to 0, and they need to go to 0 quickly. And by quickly, I mean more quickly than 1 over n. If you have an alternating series, the terms need to go to 0, and it doesn't matter how quickly they get there. They can go to 0 slowly, and it will still converge. So that's the main takeaway. Again, alternating series won't show up all the time because they have this requirement of switching back and forth. But when you see one, the restrictions on them are much easier to satisfy in order to enforce convergence than on other series.